Okay, so welcome as usual, Indoor Ag Science Cafe, and today is the second to the last of this year's cafe. And I'd like to announce that the next one is November 13th. So we are kind of squeezed, the squeezed schedule right now. Usually once every month we have this forum. And the next one is again only in 2 weeks, but there's no more cafe this year, and then cafe will be resumed in January 2019. So I hear some noise, and then again I keep muting Rijan Sheng. I keep muting your microphone here, so don't unmute, okay? So that it doesn't transmit any sound. So the today's one, Cary Mitchell is going to give a presentation, and then the next one is November 13th, and Mylan and Dan Kluko, so the father and son, is going to give their stories. So let's look forward to learning their stories in November 13th. I send out the link for the sign up the same way as usual. So with that, I guess I'm gonna stop sharing. And then Cary, you can take it over by clicking share.
Okay, I have to find my PowerPoint, which is collapsed, and right now I don't see my screen, my desktop.
Okay, do you want me to run your PowerPoint from here?
Well, no, wait a minute, I'm putting share screen.
Yeah.
And then I don't, here? Let me just see what I can, now I find it. Yeah, so now I'm bringing it up.
Yeah, I can see the PowerPoint.
Making it full. Can you see all that full screen, folks?
Yes, beautiful.
All right, well, I'll go ahead then. Good morning, everyone. Thank you for logging in. What I have to show you is going to be very image rich. So for those who are just calling in, they may not get the full benefit of this unless they go and look at the, you put these on you put these on the web for later, Cary, right? So they can always go in and see the full.
That's right.
Both audio and video?
Yeah. Right.
Okay. Well, okay. Today I'd like to give you some background regarding why I come from where I do, regarding the energy burden of plant growth lighting and controlled environment agriculture, and how I propose to overcome that. I started out 40 some years ago in NASA's space biology program, but soon expanded into its Controlled Ecological Life Support System, or CELS program, CELSS, and later its Advanced Life Support program, both of which targeted higher plants as sources of food, air revitalization, and purification of water for autonomous habitation at distant space destinations. These space-based bioregenerative life support systems were proposed to be closed with respect to mass, but open with respect to energy. And I do need to say that the funding that came with these projects was just about the only funding available in horticulture for controlled environment work at the time. So sources of energy for plant growth in space always have been problematic. And NASA has been skeptical about life support scenarios that are too energy burdensome. In this somewhat dated lunar habitation scenario, the cutaway view shows overhead lighting that looks suspiciously like HID lamps for growing food crops. There also is a hint of a solar array nearby. But because nights are 2 weeks long at most locations on the moon, solar energy without robust energy storage is doubtful. So I don't know if solar would be the answer there. In this cutaway view of plant growth shelves at a Mars base, it depicts in the background concentration of solar energy to power food production. Again, problems, prolonged sandstorms and dust storms on the Mars surface equally call this energy scenario into question. But using 1980s growth chamber and lighting technology to calculate lighting energy requirements for various vegetarian diet scenarios that the CELS program was considering for space crews led to enormous numbers of kilowatt hours for plant growth lighting and the resulting thermal control. So much so that NASA actually canceled grants and put bioregenerative life support on the back burner in favor of physicochemical methods for air revitalization and water recycling. And they still, to this day, really deflect the questions regarding where food will come from at distant space destinations. So people like me set about to try to make crops more productive on a growth area basis. One approach was to increase cropping density so that photons would not be wasted. But too much of a good thing leads to competition for light among plants within a crop stand. And light within the stand then becomes limited. In this image of a hydroponic cowpea crop stand within a growth chamber that's being overhead lit with fluorescent and incandescent lighting, all of the edible pod yield occurred on the outside of the foliar canopy. And we noticed leaf litter occurring below the canopy. Also, we noticed a lot of ab-sized flower buds and small pods within the litter. So we were losing a lot of potential productivity. When we put a quantum PAR sensor at the base of the canopy, it registered 1 or 2 micromoles per meter square per second. But outside of the canopy or at the top, it was 700 micromoles. So there was complete attenuation of light there. That waste of light prompted us to buy 15-watt fluorescent kitchen lamps, real short ones, remote them from their switches and ballasts, and we suspended them in all kinds of different geometric angles from fish line at different heights within growth compartments. And then we let cowpea crop stands grow up around the lamps. We would switch the lamps on at a given height only when the top of the stand grew to their level. So plants in the intracanopy lighting treatment on the left were much more productive than the overhead lighted plants on the right. We actually wanted to add more lamps for more productivity, but they were too thick. They took up too much space. I was aware of NASA-sponsored work at the time, growing plants with LEDs. I also knew that LEDs are relatively cool light sources, so they shouldn't scorch plants if placed within the foliar canopy. And the original red and blue LEDs tested also emitted fairly narrow spectra of light close to wavelengths of maximal relative quantum efficiency within the McCree curve. So I came up with the light sickle concept, in which slim vertical strips of LEDs would switch on from the bottom up as planophile, upright and branching species grow in height, keeping pace with the top of the crop stand and not wasting photons by lighting empty spaces above it. In collaboration with Orbitech, we developed actively heat-sinked light sickles that drew growth chamber air in through the lower end. They were hollow, and they would be pulled up the strip, they would cool the back of the diodes, and then it would go out the top into the controlled environment growth chamber. Each printed circuit light engine could be switched on or off individually, and the red and blue LEDs in each engine could be switched or dimmed individually by wavelength, making many different hues possible. On the left, the bottom LEDs, I have both the red and the blue on, and then those just above that for demonstration, we're showing just the blue on in those. So using these then, and they were interconvertible between light sickles and then arrays. So in this image of intra-canopy versus overhead LEDs lighting cowpeas, once again, our test crop, notice again leaf litter on the floor of the growth compartment of the overhead lighted plants. This is due to mutual shading of lower leaves by upper leaves, and that did not occur to any significant extent with intracanopy lighting. And that just demonstrates it doesn't matter what your light source is. If you have too much mutual shading, light level goes below the light compensation point, you're going to get premature senescence. So intracanopy won in all comparisons to overhead lighting in those tests, including biomass, energy for lighting, conversion efficiency, and even stand productivity. So while NASA was giving up on plants for life support and the funding was drying up, we teamed with Cary, Eric, Orbitech, and others to obtain SCRI funding. My part of that project was to grow the original 2-foot-long light sickles into tall LED towers that could provide supplemental lighting for high wire tomatoes in the greenhouse. And compared to overhead HPS supplemental lighting, energy costs for intra-canopy LED lighting were more favorable. As for the smaller light sickles previously, individual panels of the LED towers can be switched on separately. The wave bands are individually dimmable, and we have added another wavelength to the towers, the far red light in this case. Although all supplemental lighting treatments that we tested in those studies stimulated high wire tomato fruit yield similarly compared to the unsupplemented controls, electrical energy consumption for LED intra-canopy lighting that was integrated over entire cropping cycles from both winter to summer or from summer to winter in those experiments, that integrated energy was half or less than that for overhead HPS supplemental lighting. So that looked quite promising. Now, as you all know, Philips lighting, of course, markets their horizontal interlights, which are lower output. They are passively heat sinked, and they have fixed wavelength, waveband ratios. The actively heat sinked LED towers are more powerful, but more powerful as research tools. But for commercial application, I think they really do need to be horizontal. If I could turn an LED tower on its side, stretch it out, and redesign it, I think it could replace 2 interlights and 1 overhead HPS lamp, which is what Dutch growers use. And I think it would look something like this plan. It would move vertically upward within a row of a double-headed high wire crop as that crop grows through different growth stages. It probably would have to be actively heat sinked and could put out a lot more light at certain stages of crop development than individual interlights and maybe even the HPS lamp would. But it would replace, I think, all three lamps. I proposed this design or something similar to it for development and testing in the first of our now 4 ill-fated SCRI proposals, but the scientific merit peer reviewers didn't even notice this. They didn't even comment on it. All right, I'd like to finish up by giving you some examples of analogous technology designs for low-growing rosette crops or erectophile crops, such as the greens that are grown indoors these days. Back in my cells and ALS days, again, I grew leaf lettuce from seed to harvest in 22 days. In this image, 6-day-old lettuce is growing in homemade rain-go plastic house guttering hydroponic systems that we made from the hardware store. And during this phase of crop growth, which is in the lag phase, we were wasting lots of photons, in this case, fluorescent and incandescent photon from lamps mounted in the growth chamber. And between fixed space plants, and also because plants at this stage just don't use much light. By day 11, they were just about to go into exponential growth. So the next day, we switched on full growth chamber lighting. We started injecting and controlling CO2 higher, and we doubled the nitrogen content of our nutrient solution. By day 16, they were in full exponential growth. And by day 21, they were ready for harvest. Back in those days, we were not concerned about energy cost for lighting. We wanted to get as much productivity out of plants as possible in as short a time as possible. So now we fast forward to the LED era. How can we do this now using only a fraction of the energy we did back then? Well, LEDs are part of the answer. We know that individual LEDs are point sources of radiation. As such, the inverse square law applies for individual LEDs. Move them twice as far from plants and their intensity for the same power input drops to 1/4 the intensity, and so on. Even though beam angles of LEDs spread by a defined amount, and they are spaced close enough in arrays that the full inverse square law like this doesn't apply exactly. It does apply to a lesser extent in a modified curvilinear relationship, and we are trying to take advantage of that. So we move LED arrays closer to plants, and instead of letting light intensity go up, we reduce power to maintain constant intensity at plant level and let it integrate over time and translate into electrical energy savings. If adequately heat sinked, you can move LED arrays pretty close to crop surfaces, the limit being determined by when different wave bands no longer overlap in a blended beam, and you can see that. When canopies are not yet closed, and you are using full coverage, close canopy lighting, you can still save considerable energy for lighting, but photons still are being wasted, and so therefore energy is as well. So targeted lighting, in which photons do not fall between plants when the canopy still is open, is yet another strategy to conserve energy. And this is analogous to what we did with the original light sickles and the upward growing plants. We have demonstrated a saving of about 50% energy compared to full coverage lighting over the course of a lettuce cropping cycle using targeted lighting. So, compared to where we were back in the NASA CELS days, when our growth chamber lighting power densities were 2 to 3 kilowatts per square meter, adopting LED lighting innovations such as I've been talking about here, the power densities we need are more than an order of magnitude lower than what made NASA give up on plants a couple of decades ago. And the conversion efficiencies from electrical energy to biomass for targeted close canopy lighting are even better than for intracanopy lighting with vertically growing plants. And all of these things remain to be optimized yet. One other thing we are doing in combination with close canopy and targeted lighting, overhead lighting, is to look at different phases of the growth curve of leafy crops and not give them more or less of what they need for best productivity and maximal energy savings at any given stage of their growth. And in my last slide here, here's an example. For example, a favorable ratio of energy expenditure to biomass accumulation is hard to come by during the lag phase of growth. But after the inflection point into exponential growth, plants become and then are responsive to light, to CO2, and to other things. And they will use what you give them efficiently. But they may only do it for a short period of time. So these are some of the things that my lab is interested in, we're working on, and we're trying to do them in combination. So the combination of close canopy lighting, targeted lighting, and then what we're calling phasic optimization. So that's going to occupy a lot of our energy and interest over the next few years. I'm also interested in getting back into the greenhouse supplemental lighting and developing that proposed intracanopy lighting bar there. So with that, I will stop talking and welcome your thoughts and suggestions. So thank you very much.